On April 11, 1970, Apollo 13 is poised on the launch pad, ready to become the third crewed mission to land on the moon, targeting the Frei Mauro Highlands. The launch is nearly flawless. About 5 minutes after liftoff, the center engine of the second stage shuts down early, but the Saturn V simply burns the remaining engines longer to compensate, putting the ship into orbit. On board are Commander Jim Lovell, Lunar Module Pilot Fred Hayes, and Command Module Pilot Jack Swidert. By the time they reach 55 hours into the flight, they are coasting through the vacuum, nearly 200,000 miles away from Earth. The crew has just wrapped up a live television broadcast, showing audiences back home how they live and work in weightlessness. In Houston, the mood in mission control is quiet. The capsule communicator on duty tells the crew the ground team is, quote, bored to tears. At this moment, the crew is in the most predictable phase of deep space flight. But a routine housekeeping task is about to initiate a sequence of mechanical failures. Ground control radios up a standard request. They want the crew to stir the cryotanks. In zero gravity, liquid oxygen tends to settle, so internal fans are used to mix the contents and get an accurate reading of the remaining supply. Inside the service module, there is a hidden flaw. The insulation on a wire inside oxygen tank number 2 has been degraded by high temperatures during pre-launch testing. When the fan is powered on, that wire arcs, throwing a spark into the pressurized oxygen. The tank pressure spikes instantly. Oxygen tank 2 explodes, tearing through the side of the service module and damaging the plumbing for the remaining oxygen supply. A master alarm sounds in the cabin. Swigert reports the incident with a steady voice. "Okay, Houston, we've had a problem here." Warning lights indicate that 2 of the 3 fuel cells, the spacecraft's primary source of electricity and water, are failing as they lose their oxygen supply. Looking for the source of the problem, Commander Lovell looks out of the left-hand window. He sees a white, crystalline gas venting at a high rate into space. It is the ship's life support, bleeding out into the vacuum. The moon landing is aborted. The command module is losing power, and the crew is further from Earth than anyone has been during a crisis. With only 15 minutes of power left in the command module, the crew is forced to shut down the ship and move into the attached lunar module, named Aquarius. Aquarius is a fragile lander, designed only to carry 2 astronauts down to the lunar surface and back for a short stay. The survival math is daunting. The lunar module was engineered to keep 2 men alive for 45 hours. Now it must sustain 3 men for 90 hours. The crew faces a shortage of electrical power, cooling water, and a failing carbon dioxide filtration system. NASA has no prepared procedure for using the lander as a multi-day lifeboat. Mission Control must invent a survival strategy in real time. Reaching Earth requires pushing every system on this machine to double its engineering limits. The first problem is their course. Apollo 13 is currently on a landing trajectory. Unless they alter their path, they will miss Earth and drift into space indefinitely. They must fire the lunar module's descent engine to put the spacecraft onto a free return trajectory, looping around the moon and pointing them home. But the explosions surrounded the ship with a cloud of reflective debris. The astronauts cannot see the stars they need to align their navigation platform. Lovell develops a manual solution using the sun. By aligning the sun with a window radical, the crew establishes a perpendicular angle to Earth. They manually control pitch and roll while the engine fires, completing the course correction. Blinded by debris, the crew navigated back to Earth using a human pilot and basic geometry. To ensure enough battery power for their final approach to Earth, the crew must drastically reduce the lunar module's electrical usage. They cut their total electrical consumption down to just 12 amps. That is roughly the power used by 2 standard car headlights. To meet this limit, they shut down the heaters, the computer, and all non-essential sensors. Without heaters, cabin temperatures drop to 38 degrees Fahrenheit. Condensation coats the interior walls and windows in freezing droplets of water. Water is also needed to cool the ship's remaining electronics. To keep the hardware from failing, the crew sacrifices their own drinking supply. They ration themselves to just 6 ounces of water per day, leading to severe dehydration and a combined crew weight loss of over 31 pounds. Saving the spacecraft required pushing the human bodies inside it to the absolute edge of physical collapse. As hours pass, a silent threat builds. 3 men are filling the small cabin with carbon dioxide faster than the system can remove it. They have spare lithium hydroxide scrubbers in the dead command module, but the 2 ships use different shapes. The command module's square canisters will not fit into the lunar module's round openings. Mission Control gives their engineers a specific task: build an airtight adapter using only the materials the astronauts have on hand. Available parts included duct tape, clear plastic bags, cardboard from flight manuals, and a suit hose. Engineers in Houston build a prototype and read the assembly instructions over the radio to the freezing, exhausted crew. The crew assembles the device, nicknamed the mailbox. Taped into the ventilation system, it filters the air and brings carbon dioxide back to safe levels. The hack demonstrates the core of Apollo-era engineering, resolving high-tech systems failures with duct tape and lateral thinking. Before reaching Earth, the crew must leave their lifeboat and move back into the freezing command module for the final descent. Because the interior is covered in moisture, powering up the electronics is dangerous. Turning the batteries back on carries the risk of a fatal electrical short. But the redesigns implemented after the Apollo 1 fire included moisture-proofing for the wiring harnesses. The console holds together without arcing. As they approach Earth, they jettison the ruined service module, giving the crew their first external look at the damage. An entire exterior panel of the service module has been blown away, exposing mangled internals and tangled wiring. Seeing this wreckage confirmed the severity of the blast and validated every desperate measure taken over the last 4 days. Moving back into the command module was a gamble on a frozen, wet pod that had miraculously survived a detonation against its hull. The command module hits the atmosphere, beginning a communication blackout that lasts longer than expected due to their shallow entry angle. The world comes to a standstill. Millions watch the live coverage and lead prayers for the crew's safe return. Finally, the parachutes deploy. The spacecraft splashes down in the Pacific Ocean, missing its target by only a mile. History defines Apollo 13 as a successful failure. While the lunar landing was lost, the return of the crew remains a landmark achievement in aerospace history. The mission validated NASA's 2-ship architecture, proving that the lunar module could function as a deep space lifeboat in a crisis. Apollo 13's legacy lies in the collaborative problem-solving that brought 3 men home from the void.